Today's not an easy day. I'll throw it out there. And the reason why it's not easy is that we take everything that we did the last 2 days and we're doing a scalar version of everything today. So we got to be on the ball with all of our equations that we've done already, so that way you can digest the information I'm going to throw at you in the next half hour, 40 minutes. Okay? So to make this work, just a quick review. Are we okay with Coulomb's law? Which would be this guy down here. Do you guys have any questions with Coulomb's law? Any doubts about how you use it? Anything like that? You good with that equation? Right, so remember that this guy is a vector, it has the arrow on top. The direction is dictated by the two charges that are in the question. If they're opposites, they attract, and if they're likes repel, so you've got to draw your forces correctly. Okay? That was a lot of electric charges. Yesterday, we did electric fields, which had this equation here, which was calculating the field strength at some point in space, right? So it could be like the point right here, right? What's the electric field here? If everybody was a charge in the room, right, I'd find the electric field from each one of you at this point and add them together like with vectors, right? That's a lot of work, right? I admit that. And then this guy down here, we used mostly for a uniform electric field, right? And so for a uniform electric field, it's in between two parallel plates, so the force is constant as you move in the electric field because the field doesn't change. In a point charge field, which is this one here, the farther you are away from that charge, the weaker your force is, right? Just like gravity, right? The farther you are away from Earth, the weaker the force of gravity is. Okay? Do we have any questions with any of those things? Hunter?
When did we learn that last equation?
It was on the slideshow yesterday.
Okay.
Yeah, it was there. It was when we did uniform fields. You didn't use it for, I think you might use it for one of your homework questions last night. Just one, yeah. We didn't really do much with uniform fields because the work seems to focus on point charges more than uniform fields until we get to magnetism and then switches over to uniform fields.
Okay.
Yeah.
That one is just like the distance determines how much the forces.
Which one? This one down here?
Yeah.
So that one is, so we talked, this is an old favorite, right? F equals mg, right? So that's your force of gravity inside a gravitational field, right? We know that. So this equation here is just the electric version of it. Just to rewrite it in a different way, right? So you still have your field strength and then whatever your object is that it works on,
Okay.
right? But this one works for both fields, non-uniform and uniform, but we use it in our class mostly for uniform fields.
So you electric force and you use the charge.
So this would be, like, this E value here is like some sort of weird A field made by different charges.
Yeah.
So, and then this Q value is just some sort of charge inside that field already and what's going to happen to it.
All right.
Does that make sense?
Yeah.
Right, so with a positive charge inside the field, your force is going to be going that way. Because it goes with the field lines. But if it was a negative charge, it would go the other way.
All right.
Yeah. So this Q doesn't relate to this. Like, it's not producing the electric field. Whereas up here, this equation, the Q produces the electric field.
Yeah. All right.
Does that make sense?
Yeah.
Okay. Anybody else have any doubts, questions, things that are still kind of foggy for you before we go on? Okay. Thing pops up off the ass, but today we're going to do 4 different things. Maybe 5. We'll see how it goes. Here's kind of my thought process, just to share it with you. We're going to look at the title of today's note back here, right? Is electric potential and electric potential energy. So this is like the energy stored in like batteries and things like that in electric fields. It covers 2 chapters in your textbook. I really just kind of like streamlined everything to make it, like I picked up the important things that you need to know. And then if there's anything that you want to talk more about, I can. But I try to do the very minimum that still makes sense while you learn it. And, yeah. So the notes, I try to keep it short today. It's not like some of our other notes. It's basically the definition and then an equation. Because it's all of these questions are really more math-based. So there are 2 types, or 2 ways we're going to talk about electric potential energy today. The first type of electric potential energy, as you can see by the overall title on the slide, is uniform electric fields. So I split this class into 2 parts. We have the uniform electric field part and then the non-uniform electric field part. And they cover the same like subtopics, so electric potential energy, and then electric potential is the other one. So it just depends on how you're looking at it. So give me a second copy on the definition. Oh, not the both definitions. So here, we're looking at electric potential energy, which if you go back to our 9 types of energy we listed in our last unit, this was on our list, right, electric potential energy. I think I wrote the equations at the time, but I told you not to worry about them because we didn't need to know it until now, but obviously here we are. I highlighted here, bolded, that it's a scalar quantity, so just to remind you that it is scalar. So the equations that you'll see today look similar to the ones we've done the last 2 days, but they're all scalar this time. So even though a direction might be involved, you don't have to worry about it. The other weird thing in physics, before I show you the equation, is that in these equations, there's going to be kind of like a random negative sign at the front of the equation. And in physics, when we talk about energy, we make energies that are caused by attractive forces negative. And there's a reason for that we can talk about. I'll show you some pictures that will make a little bit more sense with pictures. But the equation for now, we have EQ. Now, don't write this down, but we have F delta D. Right? It's based on the force that, right, our work equation, right, we know force times distance. And on the last slide, we talked about what the force is for an electric field, right? That was on the last slide where your force for an electric charge is epsilon times Q. So when I put these two together, for a uniform field, your electric potential energy is the field strength times Q times the distance the charge travels in the field. So this is our equation here. And it has a negative sign in front. But we'll talk about that negative sign too. Okay, so you have negative epsilon times Q times delta D. So again, D is the same before, is the distance or displacement inside the field, right, along the field lines. So delta, I'll write it over here, so you have it. So our delta D is the displacement along field lines. So if you move in different directions, perpendicular to the field lines, but we know for work, right, force and distance to get your maximum work have to be in the same direction. And then Q is the same as yesterday, epsilon is the same as yesterday too, right? So Q is your charge, and epsilon is the field strength, whatever that might be. Any questions with anything on the slide, except for that weird negative sign? We'll come back to that in a bit. Here on this slide, I kind of try to explain it, the negative sign. There's another picture too that works too. I don't know if you want. I don't think you need to write this down. I would just like you to read it, and we can talk about it. See if that makes sense to you. Does that make sense to you guys? You feel that makes sense? You can say no, it doesn't hurt my feelings. I just find it's a very hard topic to teach because it is very weird. And there's no analogy really for gravity. So in some texts I've read, the part about gravitational potential energy, so you know that, like the very loose analogy, or I don't know if it's really analogy, is that you first have to remember that the field lines that you see here are always go from positive to negative because it's the direction a positive charge would travel inside an electric field. So the positive charges are always repelled by the positive side and attracted to the negative side, so they zip across. If you have a positive charge here on this side, that's the same as having a mass on the ground, right, your reference point. And we all know that if you want to lift this mass above your reference point, you need to apply some sort of force to lift it up. So it's the same with the charge. So if you want to move this charge away from the negative plate, then you need to, like, there has to be something there that causes a force to move it against the electric field. There has to be something, like, I would just picture again lifting something up, right? You have to lift up this to move it this way. And I don't know if you guys remember, but we talked about a question about a cat, like a really big cat in our energy unit. I don't know if you remember that slide, right? There was a big cat, and the question was about the work done on the cat as it was lifted up and lowered back down. And that question about the cat was that we said the work was zero because gravity does negative work on the cat as you lift it up, and then positive work on the cat as you lower it down. Right, so this is kind of the same thing. As you move this positive charge away from the plate, that's negative work because you're going against the field, the displacement's against the field. And then if you were to let this go, it's just like dropping something, it will zip towards this plate over here, and that would be the positive work. So going to the conservation of energy idea, right, your change in electric potential energy is going to be equal to your change in kinetic energy. And that's kind of where we're going to focus today. Okay, but it deals with all this work stuff. If you don't care about this, because I'm not going to ask you a question about why it's negative, you can just go with the fact that if it's a positive charge inside of a field, the equation, the negative sign just stays there. Sometimes I find students, we don't fully understand all the why the negative sign, like this negative sign business. They just remember when they do the math equations. You know, the last 2 days when I had you guys do math, I told you not to include the negative sign in the equations. Well, now you do it for scalars, and that will fix all your problems. So you don't have to worry about should it be negative, should it not. If you just take the equation that's on your formula page and throw a negative sign in there, then it all works out. All right. Here's some other weird equations. So I will give you. Okay, sorry. Are we okay with this equation for electric potential energy? Yeah.
I was looking at our sheet and like, which one would that be?
Actually, no, I don't think it's on there. Now that you say that, because we're gonna use the one that's on this slide for all our questions. It's great. That's a great. Until you asked me that question, I forgot that this textbook has that equation. So I didn't update my formula page. I'll do that when I'm done. Yeah. So I'll give you guys a chance to copy this down, and then we're going to talk about this too. Actually, while you got me update the formula page. Okay, so on this slide here, we're talking about something totally different than electric potential energy, even though it sounds the same. Total electric potential, which is really when you read like a battery, right? Like a double A battery is 1.5 volts, right? So when we're looking at that number, we're looking at the electric potential. So it's how much energy a charge could gain as it moves through that field. It's kind of like the summary of it. So you can see there's measured in volts, the scalar. There's electric potential, which is if you look at, again, it's tough to say with gravity, but there's electric potential where your object doesn't move, and electric potential difference where the object moves inside the electric field. So for most purposes, we always look at how charges move inside an electric field. Right? You know in a battery from some other class, or now you might be learning for the first time now, right? Electrons, when they move around the circuit, right? When they enter the battery at one end and they leave at the other, they enter the positive and leave at the negative side of the battery. And as they flow from positive to negative inside the field in the battery, they pick up energy. And then you learned in grade 9 science, or in grade 11 physics too, right? As they go around the circuit, and each load, they give a little bit of energy at each part, right? Each load has a voltage that goes with it or potential difference. So every time the electron goes through that load, the electric field by that load, the electron has to lose a little bit of its electric potential. So we're always looking at electric potential difference. So when your charge moves in the electric field, how much energy does it gain or how much energy does it lose? So that's what the difference is as it changes. It's like as I said, like gravity, there isn't really an analogy because there's nothing called gravitational potential, right? It's not a term that you have ever heard, and I don't know how you would calculate that. But what it would be if you wanted to calculate, like if your reference point again was at the ground floor of the school, let's say, then each floor, you would have a certain part of gravitational potential based on the height above your reference point. The actual gravitational potential energy depends on the mass of the object above each floor, but your gravitational potential would just be like the height times gravity. So if you move 2 floors, that would be your gravitational potential difference as you move floors, like what that change in height would be and how much energy you might possibly have. It's a very weird analogy, so you may want to forget that if you didn't understand it. Don't get too confused. So as I said, there's 2 equations here that are in your textbook, so I'll write them up here because I know it's tough to see the back. So get my So I'll put it up here. So uniform fields we had on the previous slide, E cubed, epsilon, Q, delta V. On this slide here, there's 2 ways to calculate delta V. You have delta V is equal to your energy divided by your charge, or you have your delta V to your field times the radius. So this is your electric potential difference, so that's why it's delta V, not just V. So delta V is your change in electric potential as you move through the electric field. And then it could be related to the energy your charged object gains or loses as it moves through the field, or it could be related to the field strength and how far your object travels through the field. Okay? So in terms of 1 and 2, I wrote them in order up there as they go across. So EQ, we still know is energy, and then epsilon. R is, I can put that one up there, R is the distance. So it's the distance between So your R value is the distance between the 2 plates that create this electric field. Right, so you don't know any other stats about the field. You just know like the metal plates are 5 centimeters apart or 10 centimeters apart, and it has this electric potential difference if an object was to move from one side to the other. And if you look closely at the 3 equations on the board, you can combine the bottom 2 to get the top one. Well, the D and C are, but they all kind of go together. Everything's related. Okay. So this is your typical question that you get on this stuff. So if you take a look at it, this is a harder question than it looks, maybe. This is a conservation of energy problem. So take a moment and read it, and then the system diagram is already there, but we're going to be going through all our steps for the conservation of energy. And your formula sheet might be handy to get some of the other stats that are not listed up there. All right, so here we go. So I'm going to redraw the system diagram just because it will be helpful to me. So here we go, and then it zips across. The VF on that one. If you're in your textbook, they also mention something about like you can think of electric potential, like gravitational potential, where you have to have a reference point to do all your questions too. But I'm not going to do that. They always start at the metal plate on the other, on one side and move across. What would be the energy transformation equation for this picture right here? 100?
Electrical potential energy to kinetic.
Yep, good. So we have electric potential energy to kinetic energy, right? So we have our good flow there. There's no springs involved, and there's no change in height, so we're good there. Our table of values. There are 4 quantities that we need for this question, and 3 of them are given up here. So I'll do the obvious one. our potential difference is 20,000 volts. And we're trying to find VI. What is Q and M? It's where your formula sheet comes in handy. Brent?
Q is negative 1.602 times 10 to the negative 2 joules.
Yeah, good. 19. Yeah. And what's M? Brent?
9.11 times 10 to the negative 3 kilograms.
Yep. Okay. Are we good so far? Make sense? Okay. So our next step, as we know from our last unit, right, we have EI equals EI. And we have EQ. Okay. So just as notation-wise, just be careful. Voltage is always capital V, and speed is always lowercase b. So just beware of just giving us 3. Okay. Now the next part, it goes against something I said earlier. So again, there's different ways to do this. So the way I like to do these questions is that when I know this is my energy transformation equation from electric potential energy to kinetic energy, right? I can do my math over here, but I'm not going to include the negative sign for the electron because I know it's gaining the electric potential energy as it goes across and then leaves on the other side, which is not what I told you to do earlier, which was keep the negative sign in there. Your textbook, and a different way to look at it, if you want to use a negative sign, is again still the same as conservation of energy. But the other way of looking at the question is that you have your EQI plus EK is equal to 0. So as it leaves, because again electric potential energy works a little bit differently, when it leaves the field, it's losing the electric potential energy and converting it into kinetic energy like we know. So if you use, your textbook kind of walks through the second version of this solution, and in that case you keep the negative sign in there, then it all works out in the end. The way I have it set up, and the way I do it, if you put the negative sign in there, obviously it's not going to work because you're going to take a square root of a negative number. Okay, so you have to decide what makes sense to you. And I'll help you out with that once we look at the individual charges too in a second. From this point here, I believe you guys can solve it because there's, math-wise, you guys have everything here, right? We want to find V, right? If we bring this guy, this up to the other side, we have 2 delta V Q over M equals V. So V is 2 times 20,000 times the charge divided by and it should be a really high speed, but it can't be greater than the speed of light, which is 3 times 10 to the power 8. So if you do get a number bigger than that, then you did something wrong. What is the speed of? I don't know what it is. I have 8.4 times 10 to the power 7. Is that what you guys got?
Yeah.
They're like ridiculously fast. So when this electron leaves the plate, then that is the speed that it has. So, like, just to simplify things, maybe in your mind, like this is essentially the only question that you're going to get related to any of this material. There's one that relates to the first equation that we do, but most of your math is going to be related to this. Okay. I have a different type of question, so you can read this one here. You can try this one on your own, see how it goes. It's again conservation of energy. Come around and help you out and see if you have any questions. Take the attendance too. any questions? You okay? You okay? Yeah. Thank you. One hand, you do it, bring it up, you want it? Stop away. That information. Okay. So, how would you guys like to proceed? Would you guys like 20 minutes to do homework right now? Let me do the next part of the note, or would you like to just get the note done and then have the rest of the period do your homework? I'm good either way. It's whatever you guys want to do. The next part of the note is going to be quicker than the last part.
Let's finish the note.
Because Andre says finish the note. Some people want to finish the note. Some people don't care. All right. Some people want to do homework. Yeah. So they're finishing the note. Okay. Yeah. There's only 3 slides there. So we're switching gears here to non-uniform fields. You can see the definition for electric potential energy has changed. So when you're reading this, right, the definitions change because we have 2 objects of time. So remember again, non-uniform fields means that we have 2 point charges that are working here. If you have, I don't know if your home textbook has a question, but the last textbook they had a question where it was like a triangle of charges, so there's 3 of them, and they wanted you to find the energy of the system, so you have to do it for each pair, and then just add them together. Again, the graph here, I put this here because I want to again emphasize that 2 things. Number 1, it's an inverse relationship, so as you can see, as things get farther apart, the energy between the 2 particles that's stored in the system drops, right? So we know that with gravity works, same with gravity, right? The farther you are away, the less energy you have. And then again, when things are attracted to each other, so your 2 objects are attracted to each other because they have opposite charges, it creates a negative energy. And what this is really saying is that it's trying in a different way. It's trying this graph here. The reason why it's negative is it's trying to tell you how much energy is needed to rip the 2 electrons apart. So if you were in physics, again, we don't talk about this in high school, but in university they use the idea of energy wells. Do you guys talk about that in chemistry? You know, I always wondered that. That's where I learned it in chemistry. I don't know if you care, but I'll do it anyway. And again, just going very simplistic here. You guys know from grade 9 science how you have the Bohr model of an atom, which as you learned is not the most accurate model, but it works for my purposes here. So in hydrogen, right, your electrons are stored in energy shells, and if you have your electron in the first energy or orbit, to be an ionized atom, right, or an atom without its electron, you have to remove this electron and it has to disappear, right? Get out of the atom. Does that make sense? Right? So when we talk about orbitals and energy levels, and we might talk about this in our last minute, and then I know it comes up in chemistry too. The energy associated with each orbit, you can calculate that, and they're all negative. And what that means is that out here, when your electron gets ionized, your energy, your electric potential energy is 0. So that's kind of like our reference level if you go back to gravitational potential energy. So since you're below where your energy is 0, right, anything below that's going to be negative. And from a gravitational point of view, the analogy that I was given in university was like if you're trapped in a wishing well, so down here. So here you are trapped at the bottom of a wishing well. So if your reference point is the ground, because that's what we normally do, right? Our reference point is the ground. Then if you're trapped inside the well here at the bottom, you have a negative gravitational potential energy because you're below the reference level. So what that negative represents is how much energy you need to escape the well. So if you're down there, you're 10 joules down in the well, in a very abstract way, if somebody could throw you chocolate bars to give you that 10 joules of energy to climb out of the well, good morning, then you could climb out of the well and escape and you collapse and you'd be so exhausted when you get to the top. So this negative here, right, so the analogy applies to this. So the reason why that's negative is how much energy you need to take two objects that are attracted to each other and rip them apart. So that's what we're looking at. And then once they're ripped apart or far enough away, they don't have any force of attraction on each other anymore, then they could stop moving. If they have a little bit more than that, then they keep on moving with some sort of kinetic energy. In the grand scheme of things, do you really care about anything I just said? Maybe not. I know a lot of you just want the facts. So this is what you need to know. That there's an equation. We have two charges. And the equation here is, again, EQ. We have our friend K back this time. We have Q1, Q2 over R. So not R squared, but over R. So obviously that looks the same as yesterday, but it is different. So you just have to be conscious of that. And there is a relationship between Coulomb's law and the energy. But we won't focus on that. And again, you can put a negative sign in front of that if their objects are opposite charges, or if they're the same charge, then the equation's just positive. And that's what all of our questions that you're going to see, I think, are that they're positive. The other weird one here is the electric potential. So the electric potential is a weird concept for a single charge because it doesn't really get used that often. But it relates to the amount of energy an object could have based on how far it is away from a charge. So this one has a weird equation, not a weird equation, but an equation similar to what we did yesterday, but not quite the same. We have capital V, equals K, Q, R. So V again is voltage potential, right, measured in volts, just like it was earlier in the day. K is your Coulomb constant, Q is the charge you're looking at, and R is the distance the point is from the charge. So R. So R is your distance, this point in space, this random point in space, whatever the person writing the question is asking you to find, that's what your R represents. So in the picture there, I have a charge, obviously it's negative, the field lines go towards a negative charge, and then these red circles around the charge, they're called equal potential lines. So what they relate to is that they are the same distance away from the charge. So if you do this calculation, the R is the same. So these red lines show where this V value is the same around charge. So you can see, right, because it's one charge, it circles, and because it's an inverse relationship, I don't know what the scale is for this, but they do spread out because it gets weaker the farther you are away from the charge. If you have lots of charges in an area, which is more what a scientist would look at, then you wouldn't worry about one charge, you'd worry about them all, and then you'd have to add them together. Another way to look at that is, like, yeah, so we'll look at that. This one here is just what I said. I don't think I've got this down. I don't want to. But most scientists, like if you were ever actually to use this in a lab setting, that's the only place you would use this type of calculation. You would have a distribution of charges. So you'd have a lot of different charges in one area, and you'd want to find how the electric potential is from all the different charges. So if you, like for your cell phones, again, your cell phones work with this technology. The processors in your phone will work when you touch the screen. Your electric potential changes the electric potential on the surface of the screen, and the processors figure out where you've touched the screen. So what we're going to do, because it is scalar, if you're given more than one charge, which is what you're going to be given, you literally just add them together algebraically. Like you have 5 charges, you do the same, like the calculations for each of these separately, then you add the 5 numbers together. If you're on an angle, who cares? Because it's a scalar quantity, right? So there's no components involved in this, even though the questions look the same as the field questions yesterday, but it's still a point in space above, 2 or 3 charges. And there's triangles involved to find the distances like we did yesterday, but we don't have to break anything down into components, so it makes things a lot faster. So just beware when you read the question, right? 2 things look the same, but one's a vector, one's a scalar, and if you do the wrong operation for the wrong thing, you could be doing a lot less work or a lot more work. So just as a heads up there. I see someone writing that down, so I will pause to give you a chance to do that, and then that's it for our note today. Let's look at some examples. Okay. And also, are we done?
Yeah, take them on.
Good. So I have 4 examples. We can do as many or as little as you'd like to do. The first 2 examples here are based on energy, and then the next 2 examples are based on electric potential. So we'll do 1 and 2 together. Does that sound okay with you guys? Okay. So I can treat 1 and 2 like a conservation of energy problem, because that's what it is. Just broken down into 2 steps. So in this case here, I drew a system diagram that has like before and after scene in it, right? So our before scene is question 1. What's the energy stored between the 2 charges if they're held at rest 25 centimeters apart? And then the second one is if one is fixed and the other one's allowed to move, what's the kinetic energy, or how fast is the other one moving, I guess? Yeah, that number looks weird. I don't know what. Okay, so that's what we're kind of looking at. A lot of students, when they do this question, or a similar question on a test, don't draw 2 pictures, and then usually miss one of the energies in the calculation, so you just have to be careful. Okay, so if we go through this, we have our 2 charges. 4 nanocoulombs, 6 nanocoulombs, and our distance R1 or Ri, 5 centimeters, and our F is 3. Oh, and we have mass.
Which way are you doing? Where to?
What?
Which way are you looking at? Where to?
I'm going to both together.
Are you both together?
Yeah, normally you just ask this question here. So I will still do it in parts like 1 and 2, but all my information goes with both. One thing to keep in mind, if you ever see this question, it's the only time you're going to see it. It is weird. Is I did give it the question to you in nanograms here, and nano is a billionth of whatever your standard unit is. But you have to remember when you do your unit conversion, right? So we had this in nanocoulombs, so it's times 10⁻⁹. But in masses, our standard unit is not a gram, but kilograms. So you have to go an extra 1,000 up the scale, so that's why it's -11 here, not -9 like the coulombs above it. It's a little tricky there. So for part A, or sorry, I guess before we do that, what's the energy transformation equation between these 2, like before and after? What energy do we have here for energy? Slope?
Electric potential energy.
Yeah. So we have electric potential energy. And what type of energies do we have at the bottom side there? The after scene, which relates to question 2. What energies do you think exist based on my picture? Well,
Kinetic and electric.
yep, you're right. Okay, so you have electric potential to start, and then electric potential and kinetic energy at the end. A lot of students on a test forget that the second part has electric potential as well. So just be careful when you do that because it's there. You might see a wording in the question where it says like one of the charges goes to infinity or comes from infinity, and that just means that it doesn't have electric potential afterwards, but that doesn't happen too often. So going back to what we have, in 1 we use our new equation, K Q1 Q2 over R12 or Ri, I guess we should call it. Right, and then we can just throw our numbers in, and we should get the right answer. All right, so we have K. That worked out to be the right answer. Okay, so that's A for 1, I guess. And then 2 uses our conservation of energy and just goes through the same steps that we're used to doing. All right, so I'll get you started and then you guys can finish. You have EQI before, you have EQF plus EK after. And then just depending on how you want to do it. If you already have the I before. If you didn't, it would look like this. So depending on how you want to do it. All right, that would be the long way, having all the variables, and try to work your way through and get the right answer. It's probably 13, whichever one it is. All right, last question. Do one more. This one's not too long either. You know it looks long because from a vector perspective it would take forever. But this is a scalar perspective where it happens really fast. Okay, so we'll do number 1, and then we'll go on break, and then you can come back and do number 4, or whatever else we need to get done. So you can read here 2 charges, 1 and 2, that's what they are separated by 20 centimeters, and point P is located 5 centimeters away from Q1. So it's above it, and we want to find the electric potential at Q1. Okay? So, I'll give you a second to draw the system diagram, and then we'll answer this one together. Okay, so for this question, right, it could look the same as yesterday, I don't know, but it is a 2-dimensional question, right? You can obviously see that the point is not in the same line as the other ones. However, it is scalar, so that means that the directions don't matter here. So this one has a very quick solution. So I'll show you what it is. So our first step is to find R2, right? So we still need to know that. We need to know the distance Q2 is away from point. Right, so our first step here is, as always in triangles, we have to find all the sides. Not always, but pretty close. All right, so we get this side. How far, or what is the length of that side? I have 20.6. What do you guys got? Right, so 20.6 for long step. Okay. So then we want to find the total electric potential at the point there, at point P. All right, so I'm just going to be total for total. And because it's, again, scalar, just add the 2 things together. So we find the electric potential from each thing, and then you're just going to add them together. No components involved. So when I do this, I know you can put it all in one line and do it once on your calculator to get right. I'm finding though that when students do that, so if you go right from this line here to the answer, if you did a mistake in this line here and your answer's wrong here, I can't figure out where you went wrong. So it is helpful for me as a person trying to give you part marks if you show what your calculation is for each step, so then I know how you got to that final answer. Because one of them could be right and one of them could be wrong, and I can figure out where did that happen. All right, so we'll go for a walk, and that's it for